So most of this unit is dealing with what we call trigonometric equations and identities. Now, you've already studied a limited amount of work with equations, and what we're going to be doing is extending on that a little bit today, but the bulk of the unit is going to be related to something called trigonometric identities. And trigonometric identities can be very challenging for many students to work with, even very, very good students, very academic, very skilled students in math still struggle from time to time with identities. So the first thing I want to tell you, even though we're not going to talk about identities today, is when we get to identities, which will be tomorrow, it's going to be very natural for you to be confused at times. You know, I don't think confusion is the goal. I'm not saying that. I'm saying we want to get rid of that confusion as soon as we can. To bring this full circle to where I started, that means lots of practice. Okay? Mr. Hetling and I were just talking yesterday afternoon about this, and this is how you get better at things. And it doesn't matter whether it's math or card sleights, basketball, hockey, art. You don't become really good at something by just thinking about it and then trying it. You have to practice. So, I hope that didn't scare you about this unit. I'm trying to motivate you. I'm saying you really have to be on top of things in this unit. Today what we're going to be doing is finishing off Chapter 5 before we get to identities tomorrow. We're going to be solving trigonometric equations graphically. Why graphically? Because sometimes it's just easier, and sometimes it's not possible to do it algebraically. And then we're going to be looking at modeling situations using sine and cosine functions. There's a lot of things in the real world that follow sine function patterns. Like if you were to plot on a graph the time of sunrise in Wetaskiwin over 365 days, you would discover that it follows a sinusoidal curve. At the beginning on January 1st, at the beginning of the year on January 1st, sunrise occurs very late in the morning. And then by the time you get to the middle of the year, sunrise occurs quite early in the morning. And by the time you get to December 31st, well, let's face it, there's really no difference between December 31st and January 1st other than a couple of hours, depending on the time of the day. It looks like that. And what you would discover is that it follows a beautiful sine curve or cosine curve, and we've learned that you could use either equation if you play around with the parameters to make the equation fit the data. If you take a look at the depth of water in a harbor that's on an oceanfront part of an island, the depth of water goes up and down every 12 hours because of the tides going in and out every 12 hours. There's lots of things that follow this type of curve. And that's the second thing we're looking at today. We're modeling situations that look like that. So example 1, solve this equation. 4 cos squared x minus 3 equals 0 for x equals any value from and including 0 degrees up to and including 360 degrees. We want to solve that algebraically and graphically. Now, this is a good question to start off with because this was a question on your exam Friday. Some of your exams had sine here, some had cosine, and a shocking number of people got the question wrong, even though I'm sure they felt they got the question right. They said to themselves, I'm going to work on it algebraically first, and so are you. They said, well, if I add 3 to both sides, I get 4 cos squared x equals 3. If I divide both sides by 4, I get cos squared of x equals 3 over 4. And then I take the square root, so I get cosine of x is equal to the square root of 3 over 4, which becomes cosine of x equals root 3 over 2. And I don't know, well, by a show of hands, I'm curious. Immediately to the unit circle at this point in your mind to find the locations. How many of you would use a calculator and find a reference angle? There's really no other option, I don't think. So it has to be one or the other. But there's been a mistake made here. What mistake has been made in my work? Naya? It's plus or minus. And a lot of you just solved this equation. You said, I'll come back to the plus or minus in a second, but you said that, I'm going to go under an assumption here, and I hope you think it's fair, that if you can do this with the unit circle, then you're not confused when I talk about a reference angle approach. Okay? So you would use your calculator if you had to find a reference angle. The reference angle would be the inverse cosine of root 3 over 2. You would discover that the reference angle is 30 degrees. And if you were asked to work in radians, you'd probably still do this in your calculator in degrees. It's 30 degrees, and if you were asked to do it in radians, you would write down pi over 6 instead of 30. But it's 30 degrees, and we're asked to work in degrees. Then what you would do is say, since cosine was positive, you would draw that reference angle in quadrant 1, and you would draw that reference angle in quadrant 4, because those are the two locations or quadrants where cosine is positive. And then you would say, well, my answers are these rotation angles that I'm drawing in green, and I'll write them down in a second, but you would say it's 30 degrees and 330 degrees. And by the way, those of you that had a similar question on your exam, I had one different version that had sine squared instead of cos squared. So your reference angle would have been 60 degrees. You would have had 60 and 300. But you get the idea here? So, of course, with this as a multiple choice question, there was a choice that said this, and many of you, too many I felt, I want it to be fewer. I want more of you to be successful, all of you hopefully. Too many of you chose that as an answer. But really, as Naya said, this is plus or minus root 3 over 2. When you introduce a square root, you have to say, well, it could be the positive root or the negative root. And what that means is, yes, cosine is positive, so we have those two quadrants, but cosine is negative root 3 over 2 as well, or in addition, or there's lots of ways for you to describe it, but it can be one or the other. So we have to look at both cases. And that would mean you would draw the reference angle in the two quadrants where cosine is negative, which is where x is negative. And I hate having to say this all the time, but it's important. When I say where x is negative, I'm not referring to this x. I'm referring to x on the xy coordinate grid. So this is a rotation angle theta, and this is a rotation angle theta. So that means we're going to have 180 plus 30, which is 210. And we're going to have 180 minus 30, which is 150. And the correct answer would have been those four. Okay? So that's how we solve it algebraically. Now let's solve this graphically. We have this equation 4 cos squared of x minus 3 equals 0. Now, what I'm going to show you isn't new to you. In fact, in Math 20-1 right now, well, on Friday, we are first learning how to solve quadratic equations. But they don't know about zeros yet. And they do know about factoring, but they don't understand the connection yet between factoring and finding a solution to an equation, like we do. So what I did on Friday is I said, if you have this equation, 2x squared minus x minus 1 equals 0, and I kind of joke with them, I could have fun with you and I could say, okay, rearrange that for x. I'll be working here for just a few minutes, rearrange it for x. They don't know how, right? They don't know anything about factoring a quadratic to get solutions. They can't complete the square of that. So I said what we do is we imagine that it's a function. And if I said to you, even though there's no function in the original equation, which, by the way, the original equation is this, there's no function there. There's no y. It's an equation. we imagine that there is a function, because the x-intercepts of this function are the solutions to this equation. And there's a reason for this. When you find x-intercepts, you let y equal 0. Right? That's any point on the x-axis. When you find an x-intercept, any point on the x-axis has a y-coordinate of 0. So if I said find the x-intercepts of this function, your first step would be to say, okay, well, I'm going to change that to 0 while you're solving that equation. Except in Math 20, at this point in time, they don't know how to solve that equation, so they find the x-intercepts on their calculator. So this works for any function. Right? I mean, and this is really important, I think, from an exam writing standpoint. You see an equation that you don't know how to solve it graphically if you can. What I'm saying is I can very easily use this same idea with this equation. Now, I'll be honest with you and upfront with you, I don't like the x-intercept approach. But you're expected to know that it works. So how are we going to solve this equation? We are going to throw our calculator into degree mode, because we want answers in degrees. We're going to enter the function. And now I have to talk a little bit about entering cos squared. So we have 4 cos x. We close the brackets on that, and we square it. Now, in my mind, that looks... Is that thing going again? Hissing? Okay. Can you pop the button on that white thing on the wall and turn that off? Thank you, Mr. Hetlinger. To me, that looks like you're squaring the x and then taking the cosine of x squared, but it's not. What that means on your calculator, I want to make sure that you understand this. I'll finish this first. Minus 3. What this means on your calculator is 4 cosine of x quantity squared minus 3. It means 4 cos squared of x minus 3. So it may look, if you're like me, it looks like it's only squaring the x, but it is in fact squaring the cosine. Now, what are we going to do? We are going to go zoom standard. Now, that's not zoom standard. We're going to go zoom trig. And that's not what we're always going to do, but we're going to do it in this question. So I go zoom trig, which is zoom 7. And we need to be aware of something, and I talked about this in the previous unit when we talked about just the sine x function and the cos x function. When I go zoom trig, my calculator essentially sets the horizontal window up to negative 360 through up to positive 360. If I'm in degrees. If I'm in radians, it's going from negative 2 pi to 2 pi. I believe I mentioned, but sometimes my memory is not as good as it used to be, that it doesn't actually go negative 360. It's negative 340 something, or it's negative 352.5. So if you really wanted to see up to 360, what we could do is manually go in and change this to 360. By the way, in this question, the domain is only from 0 to 360. So while we're in here poking around, why don't we just change it from 0 to 360? But I think going zoom trig to begin with is good. So now we find, let's graph it again. Now we find the x-intercepts. From an exam writing standpoint, you can see 4 x-intercepts. So you would never choose 30 degrees and 330 degrees, which was one of the choices, because it only had 2 solutions. So now we have to find these x-intercepts. And I'll remind you, you go to your calculate menu, which is second trace. You choose 0. Why are we choosing 0? Because we're finding out where y is 0. So we choose 0, and then left, right, and guess. So I'm going to start with the one very close to the beginning. So there's my left boundary. By the way, you do not have to scroll around to get to it. You can enter an x value if you're confident that it will be to the left of the x-intercept. So I just entered 10. Now I scroll. Now I scroll so that my cursor is located to the right of it. In this case, it's below the x-axis. I hit enter again. Again, I'm not sure why the guess is there. I don't think it matters. Just hit enter a third time. And it's 30 degrees. And I'm not going to spend our class time here going through and repeating the process with the other four. The other three. What you will discover is you're going to get an x-intercept at 30 degrees, 150 degrees, 210 degrees, and 330 degrees. Does that approach make sense to you? Does anybody have any questions with that? Okay, I don't like doing it that way. I would rather, I'll give you the reason for this, but when we have 4 cos squared of x minus 3 equals 0, I would rather go 4 cos squared of x equals 3. I would rather rearrange the equation so that it's not equal to 0. And then what I do is I would graph the left side as y1 on my calculator, the right side as y2 on my calculator. And rather than worrying about x-intercepts, I'm going to just find points of intersection of the two graphs. Let me do it this way, and then I'm going to explain why I prefer this. So my first function is just 4 cos squared of x. When you do it this way, you want to be careful not to rearrange it too much. The reason is if I start rearranging too much to get two different functions, I run the risk of making a mistake. Right? So I'm just moving the 3 over. And now I'm going to graph 3. My window settings should still be good. There's 4 cos squared of x. And there's y equals 3. Now I'm interested in the point of intersection, and here's why I think it's easier to find the point of intersection rather than an x-intercept. You realize that sometimes your graph goes through the x-axis in quite a steep fashion. And it's sometimes difficult to put the cursor to the left and the right. Whereas here, I don't even have to think about points of intersection and the location of the cursor that much. If I go to my Calculate menu, which is second trace, and choose Intersect, all I have to do is put my cursor close, I'll just use this one, put my cursor close to one of the x-intercepts that I care about. And then I can close my eyes and hit enter 3 times. As long as all you have are 2 functions in your calculator. If you have 3 or 4, then it gets messy. So all I have to do now is hit enter, enter, enter. I don't have to scroll around. 150. Want to know the x-intercept way over here, or the intersection point way over here? Choose intersect. Just put 10. No, that doesn't work. I guess you do have to scroll here. So you would move the cursor closer to that x-intercept and then hit enter 3 times. Not sure what happened there. Enter, enter. I don't know what happened there. Doesn't matter. I must have hit something by mistake. I think I used the same curve twice. Anyway, you can do that as well. Now, I hate to be the bearer of kind of saddening news to you, but when you take a look at your exam yesterday, this question could have been solved graphically. This question said we want, and I believe it said 4 pi. I'm sure it said 4 pi on yours. If I wanted to know the largest solution between 0 and 4 pi of that, rather than finding a reference angle and drawing it and adding 2 pi to get closer to 4 pi, I could have said y equals tan of x and y equals negative 4/7. I'm not talking about a reference angle here. I'm solving an equation. I'm going to put my calculator in radian mode, and I'm going to start by going zoom trig. There's that tangent graph that we learned about on Thursday of last week. There's negative 4/7. So if I was interested in 0 to 2 pi, then the x-coordinate here would be a solution, and the x-coordinate here would be a solution. It's where they intersect. I'm interested in the largest solution up to 4 pi. So look what I do here. X max currently says 6.15. Well, that's not 2 pi. 2 pi is 6.28, but it's close to 2 pi. I'm just going to say I want to go up to 4 pi. So I enter 4 pi. I hit enter. I don't care about anything in the negative range. In fact, I probably don't even care about up to 2 pi. But I'm going to put it anyway. So I'm going to go 0 to 4 pi, graph. Whoops. So whatever this x-coordinate is, whatever this x-coordinate is, whatever this x-coordinate is, whatever this x-coordinate is, those are all solutions to that equation between 0 and 4 pi. So I just need to find the x-coordinate of this final one, the one in black, because you were told for the largest solution. I'm not going to do that, but you could find the answer. This question could have been done on your calculator. This question could have been done on your calculator. This question could have been done on your calculator. I think that's 5 questions. The written response, of course, couldn't be done on your calculator. It could be, but you would get like fat 0 for that, right? All right, let's move on. Number 2, solve this equation over all real numbers. Now, I believe I changed your note package so it says graphically find the solutions. Am I right? Okay. You cannot solve this algebraically, or I would say I recommend not solving it algebraically. As soon as you have this kind of 2x minus 7 in here, as soon as it's no longer just x as the argument of the trigonometric function, solving it algebraically is really, really ugly. So we're going to solve this graphically. But before we do, we need to talk about the window settings, because you're not going to be successful here. You're not going to be successful in going zoom trig, because it's not just a straight trig function like cos x. It's got other parameters to it. So the first thing we're going to do, well, the first thing I would like you to do is I would like you to look at that function and, using what we learned about trigonometric graphs of sine and cosine, determine the maximum value of y of that function and the minimum value of y of that function. And I'll give you a hint. These two things are determined by looking at the value of a being 6. Don't worry about the 10. I'm talking about this function. A is 6 and d is 8. So that's going to lead you to the minimum and maximum values of y. The fact that d is 8 means, for the right-hand side, 1, 2, 3, 4, 5, 6, 7, 8, that the middle of the graph will be here. This is your d equals 8. If a is 6, then the amplitude of the graph will be 6, which means it will go 6 below and 6 above. So 1, 2, 3, 4, 5, 6. and 6 above is at 14. So this is 2, and this is 14. Why am I asking you to do that? Because what we have to do to graph this and see the solutions is manually change the window settings to reflect that. When we go, before we graph it, we're going to go into the window settings. We're going to make sure we go from maybe 0 to 16 vertically. Now the other thing I would like you to do is I would like you, and again, we're talking only about, let me make this even clearer. We are talking only about this. I don't care about the 10 yet. We'll talk about that in a second. I want you to determine the period of that graph. And you have to go back to the previous unit where we learned the relationship between the period and the value of b. And the value of b in that function is 2. Well, it's going to be pi, isn't it? Because the period is 2 pi over b, which will be 2 pi over 2, which is pi. So here is my advice, and this isn't a rule that you have to follow, as well as, but I think it's good advice, as well as setting up your window settings to reflect the min to the max, so maybe we're going to go from 0 to 16, it's always a good idea to set up your x window settings to reflect one full period from 0. So this graph is going to repeat, and quite frankly, I don't care what it looks like. It's going to repeat from 0 to pi. What I mean by I don't care what it looks like is I don't care where it starts. I don't care about the horizontal shift. I'm done analyzing things on paper. I know that it's going to go through one complete cycle, and this next part's important, between 0 and pi, and then it's going to do the exact same thing over and over again in both directions. Okay? So let's, now that we've done the prep work here, we can go into our calculator and enter the function on the right. So I'm not using x-intercepts. I'm going to be using intersection of y1 and y2. And I hope you're aware of this. It doesn't matter which one you put into which slot in your calculator. But I'll go with y1 equals 10 because that's what I wrote. And then I have 6 sine. And then inside of the argument brackets for sine, I have 2x minus 7, close brackets. I don't need to worry about factoring that 2 out. I don't care. I'm looking for solutions. And then plus 8. Now, it says over all real numbers, and now we have something else that I have to tell you. If you have an equation that is like this, or an application equation, if you do not see a degree symbol, we're talking radians. There's no degree symbol here. So, I want to back up a bit. Was there a degree symbol in this equation? No. But the domain is described as being degree-like. So that's telling you you're in degrees. I'm telling you, if you ever saw an equation and it just had the equation, it didn't tell you anything about domain, it's talking radians. Radians. So when we take a look at this question, I need to be in radian mode because there's no reference to degrees in it. So I'm going to be in radians. I want to double check to make sure I've entered things correctly. It looks okay. I don't know why I have an extra space down here. I guess that's just the way it is. I'm going to go to my window setting now. I'm going to manually go from 0 to pi. Now, you might want to go from a little bit less than 0 to a little bit more than pi. I'm not going to. So 0 to pi. The x scale is unimportant. That's just the increment. It's going to be where it puts a tick. If you wanted to be really fancy, you could say I'm going to go every pi over 4. So I should see 0, a tick, pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. And I want to go from, say, 0 to 16. I definitely want to be above and below my minimum and maximum. Well, below my minimum and above my maximum. So now I graph the scale here. Maybe we'll put 2. But the scale is unimportant. So there's 10. And it intersects there. And it intersects there. And that's it. That's one complete cycle. So now, let's find those intersection points, because it's the x-coordinate that's the solution. Go to my Calculate menu and choose Intersect. I'm closer to the intersection point on the left, so it's going to find that one. And then I repeat the process. Of course, they both have a y-coordinate of 10 because that's where the function is equal to 10, because that's what the equation is. So we have these two intersection points. Now, because I've said solve this over all real numbers, these are not all of the solutions. But I've told you that we're going to solve this over one period. So what this thing looks like, 0.528. What this thing looks like is this, but it repeats. And you'll notice that it repeats nicely, doesn't it? As soon as I drag this over, it connects neatly. And it repeats in the opposite direction as well. So if this is x equals 0.528, and the other one it was what? 1.78, and this is that, and this thing repeats every pi, then not only will they intersect at 0.53, but they'll intersect at 0.53 plus pi, 0.53 plus 2 pi, 0.53 plus 3 pi, 0.53 minus pi. In other words, what we're going to do is take the solutions that are in one period and add multiples of the period to get all the solutions. Okay. The distance from here to here is pi. The distance from here to here is pi. The distance from here to here is pi. And the reason that distance is always pi is because the period is pi. This is equivalent, everybody, in the last unit where we found all of the solutions in one rotation and then added multiples of a full rotation. Now we have to add multiples of a period. So our solutions are going to be, was it theta or x? I guess it was x. X equals 0.53 plus multiples of pi and 1.76 plus multiples of pi, where n is an element of the integers. Any questions with that example? All right, let's take a look at the next one. So there are two types of real-world application problems you need to be able to solve. One of them is one where you're given an equation, and the other one is one where you're not given the equation. So if you're given the equation here, you are simply asked to analyze this equation, and I'm not quite sure why I've covered that up, but your equation should say d of t equals negative 8 cos pi over 6t plus 18.5. Am I correct? Okay. If function notation is troublesome for you, and I hope it isn't at this level, but if you're wondering about that of t, it just means that the distance in this function depends on t. Okay, t is not being multiplied by d, it's just d. So what is this question saying? It's saying the depth of water in a harbor, in a particular harbor, can be modeled by this equation where d is the depth of water in meters and t is the time in hours after midnight. Okay? So if I wanted to know the depth of the water at 4 in the morning, I would put 4 in for t, because that's 4 hours after midnight. And that's exactly what we're going to do for A. We are asked in A to find the depth when the time is 2:50. Now wait a minute. 2:50, we need to understand time and how time is communicated, is not 2.5 hours after midnight. That's 2 hours after midnight and another 50 minutes out of the next full hour. So when you convert 2 hours and 50 minutes into hours, that's going to be 2 hours plus 50/60ths of an hour, which I think is 2.83 repeating, but I'm not sure. It is? Okay. And I've seen diploma exam questions that use this specific number, and they have multiple choices, and one of the choices is for the person who put 2.5. So be careful with that. All we have to do is put 2.5 in for t. I better show my work here. D will be equal to negative 8 times cosine of pi times 2.83 rather, over 6 plus 18.5. I don't know if I misspoke. Sometimes I do. I have a feeling I might have just said, all we have to do is put 2.5 in for t. I believe I said that. And what I should have said is, all we have to do is put 2.83 repeating in for t. Right? Not 2.5. We don't want to make that mistake. Go ahead and calculate that for me. You need to be in radian mode, because there's no degree symbol. That whole pi times the 2.83 repeating over 6, the order in which you start multiplying doesn't matter. Close the brackets, plus 18.5. You're getting 17.8? Okay. But the answer is 17.8. We didn't have to do that. Let's graph it. And we're going to need to graph it anyway for the next couple of questions. I'm going to graph negative 8 cos pi x over 6. I could go pi divided by 6 times x. It looks a little clunky, though. I'm entering the function, though. So where you divide by 6 is up to you. But, well, maybe I should not just hand wave this away. This looks wrong to me. It looks like I'm saying divided by 6x. I'm not. That's not what it's going to do. But it doesn't look right to me. So for that reason, I just like to have pi x over 6. Close brackets, plus 18.5. And I'm going to go to my window settings. Okay. This graph has a midline of 18.5 and an amplitude of 8. So it's going to go 8 above 18.5, and it's going to go 8 below 18.5. 8 above 18.5 is 18.5 plus 8, which is a little bit less than 30. I know it's 26.5, but I'm saying if we go up to 30, that should be sufficient. We could start at 0. We don't have to start at the minimum. But 18.5 minus the amplitude of 8 would take us to 10.5. So the maximum is about 26.5 or 26.5. The minimum is 10.5. We want to set our window settings up to reflect that range. I'm going to go 0 to 30. That'll do it. You could go 10 to 30. The period of this function is 2 pi over b, which is 12. Well, that makes sense. The water goes up and down every 12 hours because that's the period of tides in our world. And that means that for my x in my window settings, I'm going to go 0 to 12. I always want to go one period. Always. Maybe we'll put ticks every 2. What did I say? 0 to 30 would do it. I hope that you appreciate this comment. If I go 0 to 30, since the graph doesn't start vertically until 10.5, there is going to be some wasted space on the graph. And that means that the graph will be flattened out close to the top. Let me show you what I mean. Here's the graph. This is from 0 to 30. If, on the other hand, I wanted to go... I'm not going to do that. I'm going to have to retype it in if I do it that way. If I wanted to go, say, 10 to 30, you would find that it would be elongated more. It doesn't matter. Now, how is this helping me? Well, in question A, we want to know the depth of the water at 2.83 repeating hours. All you do is hit the trace button and enter your x coordinate, and it will locate that point. 2.8, 17.8 meters. And the reason why I'm doing it this way is when you take a look at B, I have to put it into the calculator anyway. We can quickly answer B now. B is different than A. What B is saying is, if the depth of the water is 25 meters, what is T? And that would require algebraically rearranging this equation for T. But we're not going to do it that way, because it's not just cosine of T. It becomes more complicated. All we're going to do is graph an additional function of y equals 25. You can see that they intersect in two places. That's the first place is because the water's going up at that point and it reaches a height of 25 meters. And then it goes a little bit higher and then it comes down and it also reaches a height of 25 meters. The question was, when does it first reach a height of 25 meters? So we want to find the intersection point of that first crossing of the graphs. So you move the cursor towards it, enter, enter, enter. 4.8 hours after midnight. And I've always seen these questions on a diploma exam. How many hours after midnight rounded to the nearest tenth? I've never seen it, what time? But if you were asked for the time, 0.8 hours times 60 minutes per hour is 48 minutes. So what would happen at 4:48 in the morning? I don't think that's likely that you would see that. Question C says, what percentage of the time is the water deeper than 20 meters? So we can repeat this process that we did in B, but I'm now going to put in 20 meters. And I want to make an observation to you, and this is one of the reasons why I've told you to do it this way. The width of this graph is 12 hours. It's one period, right? If you look at where the water first reaches a height of 20 meters, it's there, and it reaches a height of 20 meters again there. This is the time, the depth, I want to make sure, is greater than 20 meters. Do you agree that looks like about half? I mean, we should be getting a number in the neighborhood of, it doesn't look like quite a half, but maybe 40% or something. I don't know. I'm not that good spatially with distances. I think that's closer to a third than a half. But we need to find this value, so we could determine how long that is and compare it to 12 hours. So that's what I would like you to do first, is find those two coordinates for x. I get for the first x coordinate 3.36. It's not an intercept, it's an x coordinate. And I get 8.639 for the second. Are you with me on that? You have to somehow manage that information on your calculator to carry decimals or record them all on paper so you can retype them. I stored those two values as B and A. This is typically a numerical response question, so we don't have room for rounding here, not on a diploma exam. So I'm going to take A minus B, I guess, is the order. So 5.27 hours, 5.27 hours is how many hours during the whole cycle the water is deeper than 20 meters. Well, if we're looking for a percent, 5.27 hours out of 12 hours, if I gave you an exam with 12 marks and for some reason you got 5.27 marks right, your percentage would be found by taking 5.27 divided by 12 times 100. Of course, I can't stress this enough. If it were a written response, you'd have to show that. So 44%. I multiplied by 10 instead of 100, so I multiplied by 10 again to get 44%. So 44.0% to the nearest tenth, or 44 to the nearest whole number. We okay with that question? Evan, you getting the same thing?
Yep,
sorry.
Yep, sorry, just trying to figure something out.
No, don't apologize. I'm just checking. It's all good then? Okay. All right, so now the second type of application question is one in which you have to come up with the equation. And that's all we're going to do here. We're going to come up with the equation, but you could potentially on an exam be asked further information about the function. So we have a Ferris wheel at Westworld Theme Park, and it has a diameter of 18 meters. It travels at a rate of 6 revolutions per minute. Let's just break that down. Every 60 seconds it goes around 6 times. That's what that means. 60 seconds is equal to 6 revolutions. And we'll just park that away someplace where we can refer to it. The diameter is 18 meters, and the bottom of the Ferris wheel is 4 meters above the ground. So you climb upstairs, you get in the bottom cart, they start. Joel and Ellie start the ride at the bottom. Okay. So they get on at the bottom, and then the thing starts turning. Turns around and around and around. And what we are asked to do is come up with an equation that we could use to find Joel and Ellie's height above the ground at any point in time, which seems like an impossible task. But, I gave you a diagram, and you can choose to extend that diagram to a graph if you have room and you want to. The idea here is when Joel and Ellie start at the bottom, so they get on the cart right here. And I realize that Joel and Ellie are not points. They're people and they have height. But I'm just going to talk about that location. And that means when t is 0, they are at the lowest point, and this thing is going to spin, so they will be on their way up. At some point in time, that car that they are in is going to be at the top. And when it reaches the top, then they will then be on their way down. Which means, and this is obvious, leave it to math people to overanalyze stuff. When they get to the top, that's as high as they will go. Right? And that means that when they're at the top, they will be at their maximum height. So what we're building here is a minimum and a maximum boundary for this function. And when they get back to the bottom, they will be back at their minimum height. Now, where will they be on this graph? Where will the data be when they're at the top? Well, halfway between those two lowest points. Because the thing is spinning at a constant speed, right? It's not going faster one way than the other. So halfway in between, they are going to be at the top. Well, it turns out that this is going to be a trigonometric curve. I hope intuitively, you guys, which means without really thinking about it, you understand that the graph is not going to look like that. That's not how they're moving. What's going to happen, and I can explain this for you physics people. At this point in time, they're moving this way, which means they're not rising very quickly. Their vertical velocity vector is quite small. But when they are here, they're moving this way, which means their vertical velocity vector is quite large. Non-physics people just heard blah, 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 blah. Okay? But that leads us to the conclusion that the graph increases gradually to begin with and then more steeply, and then more gradually. So what it looks like is, we break this into 4 pieces. There's a midline, by the way. We could put this in. This is the middle of the graph. Half the time they will be above the center of rotation. Half the time they will be below. So what the graph is going to look like. Sure. Roughly, is this. And we already know how to find the equation of a function. We did this in the previous unit. We need to know A, B, C, and D. We'll look at the numbers on the left. Good morning. Look at the numbers on the left. The bottom of the wheel is 4 meters above the ground, and the wheel has a diameter of 18 meters, which means this has a value of y equals 4, and this has a value of y equals 22. Since the wheel has a diameter of 18 meters, that must mean that the radius is 9, half of 18. But that means the amplitude is 9. Now, we can do some checking here. If I take 4 plus 9 plus 9, does it take me to 22? Because if it doesn't, then I've screwed something up here. Okay, well then A is 9. Tentatively. D is the middle of the graph. Well, if this is at 4 and the amplitude is 9, this has a y coordinate of 13, which means D is 13. Does this question constrain us by telling it has to be a sine function or it has to be a cosine function? It's open, right? Well, because it's open, I'm going to make the decision to use c equals 0 and then go with a cosine function. The reason is cosine starts at the top going down. And if I reflect that, it will start at the bottom going up and match it. If I go with a sine function, I'm going to have to figure out a horizontal phase shift. And it's okay. We could do that. But we don't want to. And I'm not going to. So if I change this to -9, I have A. Now what about B? Well, B is 2 pi over the period. I told you that we were parking something here. 60 seconds equals 6 revs because we would need to use it. The period, when you look at the graph, is how far, or how long rather, I guess because it's time, how long it is from when they start at the bottom to when they get back to the bottom. Which means it's the time it takes the wheel to go around once, which is 10 seconds. The reason it's 10 seconds is we can divide 6 revs by 6 to get 1 rev for the period, and we would have to divide 60 seconds by 6 to get 10 seconds. Or, I mean, the numbers are maybe pretty obvious, eh? We can see it's 10 seconds. So that means that we can calculate B. B is 2 pi over 10, which is pi over 5. So if, and we're basically done. Here's the function. Y equals -9 cosine of B times x minus c, but c is 0, so we can just put x, which is actually time, plus 13. Just do one more thing with you. That's the answer. If you went with sine, then sine starts here going up. A would still be 9. You wouldn't change it to negative. D would still be 13. B would still be pi over 5, but you would have to use c equals that distance to shift sine from its run-of-the-mill start point to where this graph starts. And that's 1/4 of the period. You would have to add 2.5 to that point. One final thing. Let's graph this just for kicks. Y equals -9 cosine pi x, which is t, over 5 plus 13. We need to be in radians. Any application question where you create your own function is in radians. Double check it. That's what we wrote. I'm going to set up my window settings to reflect this diagram. Right? I'm going up to 10 seconds, so 0 to 10. I'm going up to 22 meters. So let's go up to 25. You should go up a little bit more. The period, I like to just go exactly one period. The height, the vertical aspect, I like to do different by adding a little bit more cushion room on both the minimum and the maximum. So now let's ask ourselves if this graph makes sense. It makes perfect sense. It matches perfectly. And now I could ask you something, if I really wanted to push you with this, I could say, what's their height 5 minutes after they got on the ride? Now, we did this in seconds, right? Because we used the period of 10 seconds. So if I said, what's their height 5 minutes after I wouldn't use 5 minutes. They're back at the bottom, right? Because they're going around every 10 seconds. If I said, what is their height 3.2 minutes after getting on the ride, you would go trace, and then you would have to enter 3.2 times 60, which would mean you'd have to extend your graph. This is only going up to 10 seconds. What's 3.2 times 60? 192? So if you wanted to know their height at 3.2 minutes, we would have to go up to at least 200 here. I think you need to be able to see the point for trace to work. And then you would go trace. It's going to regraph it now. It does not look good. They've gone around a large number of times, but it should still work. Trace, we said, did I say 192? I would recommend, the graph doesn't look like that. Your calculator's just having a conniption fit. It doesn't know what to do. It's too much going on in such a short space. You might want to see it better, go, if you know it's 192, go 180 to 200. There, I'm more comfortable looking at that. The point is you can change your window settings to answer other questions related to that function that you have created. I'm not sure why I put A and C only for question 4 and 5 in your handout. I remember doing that and saying, oh, I don't want them doing A or B and D, but I look at it now and I have no earthly clue why I said that. So these are the practice problems. 4 and 5 are just solving equations on your calculator. There's no work to be shown. 9, 10, and 13 are application problems, but you're still solving them on your calculator. So you've got about 15 minutes here. I will hand back your exams so you can take a quick peek at them. But you're not really going to have a lot of time today to look in detail at them. We will have time later on in the week. If you were interested in a rewrite for this exam, then the rewrite, I'm assuming, would be Thursday of this week, would be an ideal time. Tomorrow's too soon.